With the last class, the second topic of the course, that is matter effects, and in particular how to determine the unknowns in neutrino oscillations using accelerator neutrino data. We finished that, and now we switch gears and we talk about a new topic which is of both historical as well as current interest. Uh, just to give a short chronology of atmospheric neutrinos. The story starts with the discovery of cosmic rays. So it was found that there is radioactivity you see all around us, and there was actually a debate whether this radioactivity is coming from above or coming from below, from Earth. And I believe the question was settled by close this door. The question was settled by doing this cosmic ray detection equipment. You take it underwater, and then you notice that as you go deeper underwater, the activity falls down. So that showed that the cosmic rays are, that's justified the word cosmic rays. They are coming from above rather than coming from Earth. And second important advance in cosmic rays is considered what is called the penetrating component of cosmic rays. So once it is settled that cosmic rays are coming from above, obviously if you go to a higher place, you expect to see more cosmic rays and more energetic cosmic rays, because cosmic rays will travel through atmosphere, and during that travel you expect they will lose some energy. So to have higher energy cosmic rays, etc., and larger flux, you should go to more and more heights, and people actually set up cosmic ray experiments on mountain tops. And so it was indeed found you will find higher fluxes at greater heights, and simultaneously the theory of quantum electrodynamics was developed, and also people started to understand strong interactions better. So question asked is, what do these cosmic rays consist of? Are they electrons, or are they protons or neutrons, or are they gamma rays? QED tells us that they can't possibly be electrons and gamma rays. Why is that? I mean, you measure a cosmic ray with energy 1 GeV. If it is a 1 GeV electron, according to QED, within a very short distance through Bremsstrahlung and pair production, it should lose all its energy. And same is true also of a 1 GeV gamma ray. But it is known we are measuring 1 GeV cosmic rays on the surface of the Earth at sea level. Can they be protons or neutrons? Improvement of our understanding of strong interactions showed that that can't be true either, because the protons and neutrons, they have strong interactions, and the strength of strong interaction is much higher than the strength of electromagnetic interaction. So the Bremsstrahlung, of course, is inversely proportional to the mass of the particle. So electron will quickly lose its energy, but proton will not lose its energy so fast. But proton also has strong interactions, and the strength of strong interaction is much larger than the strength of electromagnetic interaction. So you can't, the mean free path of a proton in atmosphere, based on their understanding of cosmic rays in 1930s, it was estimated. I don't remember the exact number, but it's not very large. So it cannot be protons also. By the way, in this study there was a concept developed of primary cosmic rays and secondary cosmic rays. Primary cosmic rays are those coming from outer space, and they are protons, mostly protons, also heavy nuclei and other particles also. But then there are so-called secondary cosmic rays. Secondary cosmic rays occur because these primary cosmic rays interact with atmosphere, the nitrogen and oxygen in the atmosphere, and these interactions produce the secondary cosmic rays. And question is, what are these secondary cosmic rays?
When was it found that the primary and secondary are separate?
I can't tell you exactly, but my guess is sometime in 1920s, because this question of the penetrating component of cosmic rays, that arose by around 1935 or so. Well, I would say 1933-34.
So the primary cosmic rays, when was it found that they are protons?
Again, I don't know the exact answer. I'm sure if you read a review article on cosmic rays, all these answers will be given. But the study of primary cosmic rays is a continuing process. But I would say probably by late 1920s, early 1930s, a rough idea of the composition of primary cosmic rays, I believe, was known.
This is with balloon experiments?
No, mountaintop. I believe balloon experiments came somewhat later. I believe these are based on mountaintop experiments.
So they are primarily protons because its lifetime is very, very large.
Well, our belief based on what we see around us is that the so-called baryonic matter in the universe is mostly protons. So, and these primary cosmic rays, it is believed they are sort of some kind of leftover unbound part of the baryonic mass of the universe. Therefore, they are mostly protons, but uh, there is something called Big Bang nucleosynthesis picture, which was developed only in 1950s and 60s, based on which there is a estimate of how much of baryonic matter is proton, how much of it is alpha particle, how much is lithium, etc., etc. And people, of course, study the spectra of the stars, based on which they try to deduce how much, what part of the mass of the star is protons and alpha particles, etc. And simultaneously, they study the cosmic ray composition. So the theory plus the spectral data from the stars and the cosmic ray composition, they are all put together to evolve a picture of the elemental composition of universe, and according to which 90% of baryonic matter is in the form of protons. So, I mean, the data from the spectra of the stars and the data from primary cosmic rays, they both are utterly dominated by protons. And and also, and if you sort of try to put this information and try to do the theoretical calculation, you do get this picture that when the temperature of the universe is about few MeV, that is equal to the proton-neutron mass difference. So when the temperature was higher, the protons and electrons are combining to form neutrons, and neutron is decaying into proton and electron. Both reactions are taking place with equal rate. But when the temperature falls to 1 MeV, the proton and electron, they don't have enough kinetic energy to combine to form neutron, whereas neutron can still decay into proton. But on the other hand, neutron can also combine with proton to form a deuteron, and somehow two deuterons can combine to form alpha particle, which is a very stable particle. So one looks at this thermal history and calculate the abundance of helium in the universe, and that thermal history and that so-called Big Bang nucleosynthesis calculation, it matches what we see about the amount of helium in the universe, in the form of helium in the stars versus and also helium in primary cosmic rays. So there is three ingredients: theory, data from stellar spectra, data from primary cosmic rays. These three are put together to build a picture of elemental abundances in the universe.
The data from primary cosmic rays, they are from mountaintop experience or satellite or?
No, not quite. Okay, nowadays satellites, but even now mostly mountaintop experiments, and I believe now only very few groups are doing balloon experiments. But satellite experiments, of course, are expensive, and the exposure they can have is limited. So it is my impression that the data in the studies of primary cosmic rays is dominated by mountaintop experiments. So this penetrating component of cosmic rays, that was a very tricky problem which was facing the physics community in early 1930s, and this is a problem to which Homi Bhabha actually he studied it. His one of the people who devoted a lot of attention to this problem, and I believe it was his study which concluded that the primary cosmic rays, this penetrating component can't be is not electrons, not protons. So he hypothesized that it's some other particle. What other particle could it be? There was no theoretical consensus, but in 1937, again in a mountaintop experiment, Anderson and Neddermeyer identified this new particle, which was called, now it's called muon. At that time it was called something else. And just a couple of years before, Yukawa proposed that there should be, and also identified muon with mass of about 100 MeV. But just a couple of years before, Yukawa claimed that there should be an exchange particle of strong interactions between a proton and neutron, which should have a mass of 100 MeV. So people thought it is this particle. They have found Yukawa particle. And in fact, I believe it was Homi Bhabha who suggested the name mesotron. So its mass is between mass of proton and mass of electron. And meso, I believe, is a Greek word for intermediate. So since Bhabha suggested the name mesotron for this particle, but it was soon shortened to meson. But a deeper study of this particle showed that it had none of the properties expected of Yukawa particle. First thing, that it has no strong interactions. And also Yukawa particle was predicted to be a scalar, and this turned out to be a spinor. So, I mean, what is the purpose of this particle, so to speak? There is a famous comment by a very well-known physicist called Rabbi. So, when these properties of muon were shown, he asked who ordered that. Basically, what is its purpose in the scheme of things? And that is a question we are still facing. I mean, why are muon? Except that now we ask the question, why is there a second generation of particles? Why is there a third generation of particles? But so we don't have a very satisfactory answer to those questions. But this spin half particle, which was discovered, which was identified with this penetrating component of cosmic rays, it's a spin half particle with electromagnetic and weak interactions. and with a mass of about 100 MeV.
Sir,
Yeah.
one question.
Yeah.
At that time, we have only muon sources from the cosmic rays itself.
Right.
How do we measure the spin? How do we conclude that spin half?
I believe by that's a good question, and strictly speaking, I don't know the exact answer. But I believe by looking at the distribution of, by looking at the electron energy, and also by that time we have this Fermi theory of beta decay, and so by combining, by trying to build a theory of muon decay into electron, and sort of comparing the predictions of the electron spectrum with experiment, I believe that was consistent with what was observed. So it's a mixture of theory and experiment is my guess, but how exactly its spin was determined to be half, I can't tell you exactly. I mean, I can give some guesses, but I don't know the exact answer. One has to dig through the papers of late 30s to find out exactly how that is done. But as I said, it was indeed established that it's a spin half particle rather than a spin zero particle. So we have this muon whose role in the scheme of universe we don't understand. And oh, by the way, one additional thing that Homi Bhabha did. So even after muon was identified, there was a puzzle. The puzzle is the lifetime of muon is 2 microseconds, and even if you assume that muon is traveling, let's say, with 99% of speed of light, the distance it can travel in 2 microseconds is about 600 meters. But the thickness of atmosphere is about 10 kilometers. So you assume that at the top of the atmosphere, the primary cosmic ray interacted with an atmospheric nucleus, produced the muon, and the muon has traveled 10 kilometers. Whereas, and because we do see muons on the at sea level, but according to this, the muon should decay within 600 meters. So that was another puzzle, and Homi Bhabha explained it based on time dilation. The 2 microseconds is muon lifetime in its rest frame. But in the frame of the Earth, this muon has energy of 1 GeV. So it has a gamma factor of E by m, which is about 10. And from relativity, we know that something in its rest frame has a time interval tau. If you go to another inertial frame, then that time interval is dilated by this factor gamma. So in Earth's rest frame, in the frame of Earth, the muon lifetime looks to be gamma times tau, which means C gamma tau will be 6 kilometers rather than 600 meters. And fine, you can imagine, say e power minus something. So 6 kilometers, it will fall off by 1 over e, but at 10 kilometers, it will fall off by, I don't know, 1/4 or whatever. So there is still enough flux at sea level. So this is probably the first experimental demonstration of the fact of time dilation, which was proposed by Einstein some 30-40 years before. By the way, so as I mentioned, Yukawa proposed his particle, which is a scalar and which is strongly interacting. But as I said, this muon, it was shown that it doesn't behave like Yukawa particle. So the search for Yukawa particle continued, but unfortunately, Second World War intervened. I believe there is a professor at Calcutta called D.M. Bose, who continued he's quite well known. In fact, he started his research in 1920s or so. And in the 1940s, as the war was being fought in Europe, he was isolated enough from the war that he could continue his cosmic ray researches. And apparently, he was doing cosmic ray experiments in Darjeeling, where he developed a technique based on photographic emulsions to catch cosmic ray decays which occur at time scales smaller than microseconds. Unfortunately, the kind of equipment he had was not quite it couldn't, I should say, what one needed to measure was time scales of the order of tens of nanoseconds, and his equipment couldn't quite measure up to that. So there was no new discovery in his experiment. But after the war, his technique was used by other people, and of course with better photographic equipment. And sometime in 1948 or so, a British physicist called Powell discovered what we now call pi, whose lifetime was, I believe, something like 50 nanoseconds. And pion satisfied all the constraints that one would impose on Yukawa particle. So actually, the Nobel Prize was first given to Yukawa and only then to Powell. Now, people then did further studies of these secondary cosmic rays, and then they observed what we call strange particles. among them the strange mesons. All these were done in these cosmic ray experiments at mountain tops. So then, having discovered all these particles, then people studied their properties in detail to understand their method of production and method of decay, etc., etc. And in fact, it is the decays of K plus and K minus which led to the proposal of parity violation. And later, it is the studies of K0, K0 bar decays where CP violation was discovered, and various other important developments took place. And one important development which should be noted is it also led to reviews of particle properties. You all, I hope, know of this. Okay, it's called PDG. So, I mean, there are all these particles, and each particle has so many decays, and it is difficult to sort of keep track who is doing what. So, a bunch of people informally formed an informal group and decided that okay, every year they will set aside 1 month of their time to gather all the data together and put it together in the form of a book. And that is how this reviews of particle properties started, I believe in 1960 or so. And since then, of course, it has become a very big business. I believe they were probably inspired to do this because of the study of the parity violation. Actually, the Yang and Lee proposal for parity violation was actually possible because of some similar effort made by a single person. There is a Swedish physicist called Siegbahn who has systematically collected all the data available on alpha decays, beta decays, and gamma decays that was available, let's say, as of 1952 or so, and he compiled into a radioactivity handbook. And so Yang and Lee, while they were struggling with the problem of this kaon decays, they wanted to know what proof there is that parity is conserved in weak interactions. And if they had to consult all the experimental data that was available, probably they would have spent their lifetime on it. But thankfully, this Professor Siegbahn has compiled everything in one book. So they spent a few days rather than a few years going through this Siegbahn's book, and they could see that there was no evidence anywhere as far as Siegbahn's reference is concerned. There was no evidence that parity is conserved in weak interactions. So they made this proposal that parity is not a symmetry of weak interactions. And of course, then various ideas came up about how to test that hypothesis, and 3 different experiments more or less simultaneously showed that yes, parity is not a symmetry of weak interactions. So, And one of those experiments was the decay of pi plus 2 mu plus mu mu. So pi plus is, we know that pi plus is spin 0, mu plus is spin half. So if parity is conserved, mu plus should come out with 50% probability, it should come out left-handed, and with 50% probability, it should come out right-handed if parity is conserved. And what this experiment, there were two independent experiments, but the first one was done by Garvin, and by looking at the decay distribution of the electron relative to the muon direction, you can figure out the spin polarization of the muon. And this experiment, which took only a few days to perform, they could show that the muons, the mu pluses in this decay are preferentially right-handed, and hence parity is not a symmetry in this decay. I don't know how many of you know of this textbook. There is a well-known quantum mechanics textbook by Ghatak and Loknathan. It's one of the very good textbooks in quantum mechanics. And Professor Loknathan was a professor at University of Rajasthan, Jaipur. And I met him at a conference sometime in the late 80s, and he told me this story. It seems he was a PhD student at Columbia University in late 50s, and he shared an apartment with this man, Marcel Weinrich, who was also a PhD student. And one day, Weinrich comes home in the evening and tells Professor Loknathan, "Today we proved that parity is not a symmetry of weak interactions."
So this was before Madame Wu experiment?
Well, it so turned out Madame Wu was a professor at Columbia University, and Garvin and Lederman were also professors at Columbia University. But Madame Wu's experiment required advanced cryogenic apparatus to keep the those cobalt 60 spins aligned. So I believe actual experiment of Madame Wu probably was done in Washington, because all her collaborators are from National Bureau of Standards in Washington, and they, I believe, developed the cryogenic system. So where exactly Madame Wu's experiment took place, whether it took place in Columbia or in Washington, I don't know. I would guess in Washington, because the cryogenic system was the responsibility of the Washington group. But I believe Madame Wu's results and the results of this experiment, they were published sort of in the same issue, I mean, one after another in the same issue of Physical Review. By the way, the same experiment was also independently done by a group at University of Chicago. Uh, for us, this decay is important for as far as atmospheric neutrinos are concerned. So anyway, with all this backstory, let us come to what is important for us. That is so you have a proton. Primary cosmic rays are mostly protons, so that's why I am writing proton. But in principle, you can replace it by an alpha particle or a heavy nucleus. Things will not change much. Will hit a atmospheric nucleus. This is either nitrogen or oxygen. In atmosphere, those are the two dominant gases, and both are strongly interacting particles. So, and if this proton has a high enough energy, it will break up this nucleus, and there will be a lot of protons and neutrons. Plus, in addition, you have pions, kaons, etc. So, how many pions are produced, how many kaons are produced depends on how energetic this proton is. But one simple reaction which will take place is through the delta resonance, which will be, let's say, proton plus n prime. So, one proton in this nucleus is excited into a delta resonance, and that delta resonance decays into a into a neutron and a pi plus. So that's why I have an n prime here. This interaction can be excited even by low energy protons. Whereas if you want large number of pions and kaons, then of course the proton energy has to be very high.
What range of energies we are talking about for the proton?
I mean, this interaction can happen if the proton has energy of, I don't know, 200, 300 MeV. Whereas, if you want to produce a kaon, proton should have an energy greater than 1 Joule.
And what are the average energies of the primary protons?
Oh, average energies are quite small, but the actual number of cosmic ray particles is quite huge. So, even if you are in the tail, you have enough number of even you have enough production of pions and kaons. So we are primarily interested in pi plus minus, k plus minus, k0 bar. So pi plus decays into mu plus mu, and pi minus decays into mu minus mu bar, essentially with 100% branching ratio. There are other modes, but those other modes are less than 1%. So it's essentially 100%. K plus 2/3 of the time it decays into the same two body mode, or it can decay into pi 0 mu plus mu and pi 0, and also there are pi plus, pi plus, pi minus, pi plus, pi 0, and there are also all these purely strong interaction modes are there, and these three body semi-electronic modes are there. But basic point is you have pi pluses and pi minuses, which again will decay into muons, pi zeros which will decay into two photons. So the only objection is this mode where you are directly getting an electron, but the branching ratio for this, I don't know, maybe 5% or so. And the kaon production is suppressed compared to pion production. So the contribution of this to the overall neutrino production is not so high. So the basic point is that no matter what kind of meson you produce, eventually you get a muon. And a muon, once produced, decays into this is not a 100% accurate statement, but it is statistically, this is a very valid statement that for every meson that, or I shouldn't say for every meson, that in atmospheric neutrinos there exist two new mu's for every mu. By the way, in making this statement, I am saying, when I say nu mu, I am actually thinking of neutrinos and antineutrinos together, and when I say nu e, I am thinking of electron neutrinos and electron antineutrinos together. If you try to make a distinction between neutrinos and antineutrinos, things are more complicated. And there is a reason why I am putting neutrinos and antineutrinos in the same basket. I will come to that in a minute. But if you allow me to put neutrinos and antineutrinos in the same basket and collectively refer to that as neutrinos, then I can make this statement that in atmospheric neutrinos there are two muon neutrinos for every electron neutrino. Of course, that statement is based on the assumption that the muon is decaying in the air. But if the muon energy is very high, muon will not decay in the air. So this statement actually is true only for lower energy neutrinos. I mean, when do I get a high energy muon? I get a high energy muon when the pion energy is very high. If the pion energy is very high, then the neutrino energy is also very high. So If I go to very high energy neutrinos, this statement may not be true. But below neutrino energies of 1 GeV, we can say that there are 2 muon neutrinos for every electron neutrino. What's the time?
11:12.
Okay, so we'll continue for another till 11:30 or so. Now, sort of, let's indulge in bit of digression. In 1974, two different groups, Jogesh Pati and Abdus Salam on one side, and Sheldon Glashow and Howard George on the other side, they both proposed what are later called Grand Unified Theories or GUTS. The idea in these theories is that in standard model we have three gauge groups, SU3, SU2 and U1, and each gauge group has its own coupling. The idea behind Grand Unified Theories is that there is at high temperatures or high energies, there is only one gauge group with a single coupling, and due to spontaneous symmetry breaking, that larger gauge group broke up into these smaller gauge groups, and there is an idea called renormalization group running of coupling constants, and that renormalization group running made the three coupling constants different from one another at lower energies. That is the basic idea of these Grand Unified Theories, and this idea sort of caught on like a wildfire, and there were hundreds of papers written on these ideas. But question is, how do you test it? And one very important prediction made by Grand Unified Theories is proton decay. Now, as Raj commented earlier in the class, that proton is a stable particle. Why should proton be a stable particle? Because we see examples all around where a heavier particle decays into lighter particles. Muon, which has 1/10 of the mass of proton, it decays. Pion, which has 1/7 of the mass of proton, decays. Kaon, which has half of the mass of proton, decays. So why doesn't proton decay? We have no answer.
Can we say that it is because we don't have any Feynman diagram which allows it to decay? Is that an answer?
Yeah, see, there are for these kinds of questions, there are you can answer them in sort of two ways. One, of course, you can say that that's the answer you have just given, that we do not have a theory which allows proton to decay. But now let us try to imagine a theory in which what kind of characteristics should a theory have which allow proton to decay. That's one question we can consider. But before that, let us consider a somewhat more basic question. This is a principle you have in quantum mechanics, that everything that is not explicitly forbidden must happen. And to give you an example based on what we have already studied, before neutrino oscillations, we had, even now, this decay mu to e gamma is not seen. Before neutrino oscillations, the explanation given was the muon lepton number is conserved, electron lepton number is conserved, therefore this decay will not occur. But now we have neutrino oscillations, and we have seen evidence that mu is oscillating into mu e. So we know that muon lepton number is spontaneously converting into electron lepton number. So even if my theory does not have a term in the Lagrangian which couples muon to electron, the fact that my theory should allow this, if I build a theory which explains mu conversion to mu e, the same theory will predict mu to e gamma to be non-zero. It only says it's non-zero. What is the value? To know the exact value, I should have an exact theory. So I can build a theory which gives me mu to mu e oscillation and predicts mu to e gamma branching ratio of 10 to the minus 60. It's very trivial to build such a theory. As far as experiment is concerned, 10 to the minus 60 is equivalent to 0. But mathematically, 10 to the minus 60 is non-zero. So
the muon to electron, that decay written there, it is not seen in experiments.
Yeah.
And it is not, earlier we used to say that it is not allowed because muon lepton number
is conserved and electron lepton number is conserved.
But due to neutrino oscillations,
we can no longer say that.
But still the system that we have in place does not allow for muon to electron.
No. All I'm saying is so we had electroweak model with zero neutrino masses. So when zero neutrino mass electroweak model has mu to e gamma exactly equal to 0 and no neutrino oscillations. But now I have observed neutrino oscillations. So I am compelled to put in neutrino masses. How I put neutrino masses in my theory? There are 100 different ways. But I choose the simplest possible way by putting Dirac masses into electroweak model, just as I put electron mass, quark mass, etc. It's not an attractive way, but logically it is allowed. I do that. Now, my theory with my electroweak model with neutrino masses explains mu to mu e oscillations. and it predicts a non-zero value for mu to E gamma. Even my Lagrangian doesn't really have a mu to E gamma vertex in. There is no such term in the Lagrangian. But due to second order effect, third order effect, whatever, mu to E gamma will arise. And I have now a well-defined theory. In a well-defined theory, I can do any calculation I want. And when I do the calculation, the branching ratio comes out to be 10 power minus 60. Experiment wise, it is 0, but mathematically, it is non-zero.
Now there are mu to E conversion experiments looking for, right?
Yeah.
Is that related to neutrino mass models?
Yeah. So the basic idea is we have seen individual flavor violation in the neutral fermion sector, in neutral lepton sector, and hence there must be individual flavor violation in the charged lepton sector also. Now, to find out how exactly the flavor violation is to be introduced, we need to understand the interrelation between the flavor violation in neutral leptons and flavor violation in charged leptons. If we see both of them put together, we can build a theory which will give us, if both informations are available, then the available theory space becomes much narrower. So that is why mu to E gamma, people are searching for mu to E gamma, Higgs to tau mu, all kinds of charge flavor violation searches are going on. But as I said, if something is not explicitly forbidden, it must be allowed. And nobody has ever seen a proton decay. So in order to make proton absolutely stable, people just invented a symmetry called baryon number symmetry. So according to this, proton, neutron, lambda, ... they all have baryon number +1. And their antiparticles have baryon number -1. And you just declare by fiat that baryon number should be conserved in all interactions. What is the proof that this is so? One, of course, is all the decays that we have seen, they conserve baryon number, and the most dramatic proof is antiproton production. So, Dirac theory predicted that for every particle there should be an antiparticle, and for proton the antimatter particle positron was discovered in 1932. So for proton there should be an antiproton with the same mass. So producing and identifying an antiproton was a challenge. How do you do it? Can I have an interaction like this? Energy conservation wise, angular momentum conservation wise, all those, this interaction is allowed. But this is not allowed by baryon number conservation. To make it by baryon, to conserve baryon number, the final state should be like this. And this is one of the famous problems people work out to understand relativistic kinematics. and if this is a projectile and this is a target, so this has coming with non-zero energy and this is stationary. For this reaction to take place, the energy of projectile should be greater than 7 times the mass of the hole. So, to produce a 1 GeV particle, you need projectile energy which is some 10 times more, and that is being imposed on you by this baryon number conservation. But people started entertaining ideas of baryon number non-conservation due to some developments which took place in 1964. The cosmic microwave background was observed, and of course CP violation was observed. And what this cosmic microwave background showed is that universe is expanding. And in 1967, a great man called Sakharov he wrote, I think this is something like a 2 or 3 page paper, but it's one of the most influential papers. He wrote 3 conditions under which you go from a matter antimatter symmetric universe to a universe with only matter. First condition, matter, at least as far as Sakharov was concerned, was essentially baryons. Of course, people were speculating about dark matter, but that got really established later. So, matter antimatter symmetric means initially there are equal number of baryons and antibaryons. So, baryon number of the universe is 0. But presently we see only baryons, so baryon number of the universe is non-zero. So, there will have to be baryon number violating interactions. Otherwise, this cannot happen. Second is you need CP violation. CP conservation means the rate at which delta B equal to positive interaction and the rate at which delta B equal to negative interaction, they both occur at the same rate. That's what CP conservation says. So even if I put in baryon number violation, the rate at which B is going down and the rate at which minus B is going down, if they are the same, net B will still be 0. So you must also have CP violation. And third, no thermal equilibrium. If the forward reaction produces delta B is positive, reverse reaction produces delta B negative. And if there is thermal equilibrium, even if there is CP violation, if there is thermal equilibrium, then I cannot produce net baryon number. And the discoveries in 64 showed that there is CP violation, and expansion of the universe means that there is no thermal equilibrium because the universe is cooling down all the time. So, in order to realize a universe with non-zero baryon number, starting from a universe with zero baryon number, only thing that is needed is a baryon number violating interactions. So this is, I would believe, one of the primary motivations why people started entertaining constructing theories with baryon number violating interactions. And the grand unified theories that I mentioned, they contain baryon number violating interactions. And by what I mentioned before, if something is not explicitly forbidden, it must occur. So a theory with baryon number violating interaction necessarily predicts proton decay. So in a universe with baryon number violating interactions, proton is not absolutely stable. You can give it a large lifetime, 10 power 10 years, 10 power 20 years, 30 years, 40 years, whatever. But you cannot say that proton is absolutely stable. And the simplest grand unified theories predicted that proton should have a lifetime of about 10 power 28 or 29 years. So that was sort of considered a signature of grand unified theories, and experiments were built to look for proton decay. And in the next class, we will talk about those experiments and the different directions those experiments carried us as far as development of physics is concerned. Okay, I'll stop now.
Is there a ratio between the number of muons and cosmic muons at our level, sea level, versus the neutrinos?
Yeah, I believe there is in particular, there is this group in Japan, Honda et al., who calculate atmospheric neutrino fluxes, and in order to improve their predictions of atmospheric neutrino fluxes, they actually measure the number of muons at various different heights, at sea level, at sort of, 100 meters, 500 meters. So they actually developed a parallel program to Super Kamiokande detector of measuring the muon flux at various different heights and use that as an input I mean, they have a Monte Carlo program which simultaneously predicts the neutrino fluxes and muon fluxes, and they keep adjusting the parameters of this program so that the predicted muon flux matches the experimental observation, and then see how the neutrino flux is adjusted. Yeah. So certainly the measurement of muon flux not only at sea level but at various different heights is an important input in the prediction of atmospheric neutrino fluxes.
One more question, it is not much related to neutrino physics, but something related to the matter-antimatter asymmetry. So, we are saying that we need three conditions. First one is baryon number violating.
Three necessary conditions, I should have emphasized that. Yeah.
So in this case also, we are assuming that in the beginning there is equal number of matter-antimatter.
Yeah.
But we are just, I mean, why do we assume that?
There are in lot of these things there's always the requirement of elegance.
So even if you assume that, I am just saying that we are still starting with something, right? We are not really minimizing anymore. I mean,
yeah, no, I agree with it, but see, there is as I said, it's in some sense a somewhat artificial condition of elegance or naturalness, but there is a ratio called number of baryons to number of photons, and that number is 10 power minus 9. So if you want to build a universe, if you want to build a theoretical model of universe which looks like the present universe, and where there are no baryon number violating interactions, I have to assume a value for nb by n gamma. And suppose tomorrow you build a model where nb by n gamma is 1 at the beginning of the universe, and today it has become 10 power minus 9. I'm sure people will be quite happy about that. But based on what we have, the picture of early universe we have today, this nb by n gamma, it is 10 power minus 9 now, but at earlier universe it will probably be even smaller. So it's always a small number. So where is this very small number coming from? You need to explain that. And so far nobody has a satisfactory explanation as to where that small number has come from. So the other assumption people make is that it actually originally it was 0, and due to baryon number violating interactions, somehow this small number has developed. But another possibility is you assume it to be 1 and somehow bring it down to 10 power minus 9. That's another possibility, and if somebody can build a theory with baryon number conservation, and somehow the expansion of the universe made the number of photons larger so that 1 became 10 power minus 9, and you build a theory which is consistent with all other experimental data, that is an equally viable theory, and I mean, I'm sure there are a lot of people who would even like such a theory.
for me, like the questions like why we have three generations.
Yeah.
That's like a more clear-cut question because we are doing experiments and we have seen the three generations.
Yeah.
But when we come to this cosmological arguments,
Hmm.
I feel like there are many parameters which are.
Yeah, I mean, when you go to cosmology, there are a lot more, there is a sort of a lot more space to play around with. But of course, in order to be able to make a proper theoretical analysis, you need to sort of constrain yourself a little bit. Because if you say everything goes, then you really don't have a way to analyze things.
One more question.
Yeah.
Not related this lecture directly.
Hmm.
It's about neutrino masses. So we have Catrian experiment measuring nu e mass. Then we have what other ways we know the mass. One is oscillation. So we know the delta m squares. The third is there are arguments based on cosmological arguments.
Yeah.
So I think that gives the lowest bound, right?
Right. Yeah.
So I have no idea how that bound comes. So in some lecture, if you can.
No, I mean, if I have to read up a lot to explain it. I have not really followed those arguments, but in a somewhat hand waving way, is that, I mean, we have measured so-called energy density of the universe, and it's the evolution of the universe is affected differently by relativistic particles and non-relativistic particles. The relativistic particles affect the evolution of the universe one way, non-relativistic particles affect the evolution of the universe in a different way. And neutrinos are relativistic. So the assumption is that, so based on the expansion of the universe that is measured, etc., there is an upper limit on the energy contribution made by relativistic particles to the energy density of the universe. And that number you translate into neutrino mass. That is roughly how it is done. There are a lot more details, but in a hand waving way, that is how it is.
So the reason why I asked this is because it seems like Catrian experiment even after 5 years will not reach this bound.
Yeah.
So I am hoping that Catrian will somehow get a bound and the cosmological thing is wrong. That is my personal.
Yeah. I mean, there are a lot of people who don't quite like the cosmology arguments, because in cosmology you are compelled to make some assumption. I mean, a large number of those assumptions are quite natural, and one shouldn't crib about making those assumptions. But any cosmological conclusion is based on some assumption. That is, given the nature of cosmology, I mean, I guess that's how it goes. Okay, so we'll meet next Friday at 10:15.